To R2E and welcome to the next video, that is on second order differential equations. And just a heads up before I jump into the video that this is just a theoretical videos and I'm not doing a lot of problems in this video series. I'll be mainly introducing to the techniques, and if you want to practice a little bit or want to see some interesting examples, you can go to this Shepley Ross. I think it's Shepley L. Ross. He has a book on differential equations. And or else I will suggest G.F. Simons. He also have a book on differential equations, and this one is actually my favorite one, G.F. Simons. And today the part I'll be teaching is also from the G.F. Simons. But before I jump into the main content, I should also introduce a concept of Wronskian that I left in the last video while talking about linear independence. I should have talked about it at that time, but unfortunately I didn't. So let's talk about Wronskian. So a Wronskian is a mathematical tool which will immediately tell you if two solutions are linearly independent or not. Right, so that's the definition I would like to give, and it's defined as determinant of a matrix that contains y1 of x, y2 of x, and then their derivatives. And this is for a second order differential equation. So for a second order differential equation, you have a Wronskian like this. For a third order differential equation, your Wronskian will look like this. So y1 dash of x, y2 dash of x, and y3 dash of x, and y1 double dash of x, y2 double dash of x, y3 double dash of x. Alright, so this is the Wronskian, and if your Wronskian is equals to 0, then your solution is not linearly independent, and if your Wronskian is not equal to 0, then it is linearly independent. Alright, so this was the brief idea of Wronskian. Because in my series I'll barely be talking about Wronskian. Just for once or twice I will talk about Wronskian or ask you to check whether two solutions are linearly independent or not. But and in lot of textbooks also, you will not when they will start their discussion on second order differential equation, they will talk about linear independence and all this stuff, and there they will introduce the Wronskian. They will ask you to check it, but later on you will not see Wronskian a lot in actually computing the solutions. But in rest of the theories you will see. The theory of differential equation is a little bit one part of it is about computation, and other part of it is about knowing the solution, understanding the solution. So right now we are talking about not knowing the solution, getting to how to compute or get to the solution. Alright, so let's pick up from the last idea we used in the second order differential equations. That was that if I have a differential equation given as a of x, y double dash of x plus b of x, y dash of x plus c of x, y of x equals to 0. So and if a of x, comma b of x, comma c of x are constants, then e to the power mx is a solution to it, right? This turns this the second order differential equation to a second degree polynomial that may look like some am square plus bm plus c equal to 0, and all you have to do is solve it and get two values of m1 and m2, and you will have your solution set that will look like e to the power m1x and e to the power m2x. And if say m1 and m2 are equal, then you will have your solution set that will look like e to the power m1x, sorry, e to the power m1x, sorry, x e to the power m1x. Alright, so this will be your solution set. Now let's extend this idea to say nth degree, to a nth degree differential equation with constant coefficients. So I'll make a claim here that dE given as d x y dash, okay, first y should come actually, y double y dash, y double dash, and so on till yn, and that may be given as something like summation equal to 0 to n ai y to the power I in brackets equal to 0, where yi is given as di upon dx. Sorry for this. Yeah. So then with all ai's constant, then e to the power mx is a solution of above dE, right? So this is a solution of above dE, and once you solve it, you will have a set S that is contains m, so on mn, and for each m that belongs to S, you will have a solution in the form of y mx, right? And that will satisfy the above dE. Now there is one more thing about this differential equation that I should tell you, that I should say, at this point. Yeah. And if, say, out of n, say some r have equal values, are equal, say some r are equal, right? So we will have our solution as something like e to the power m1 x, so on, e to the power mn minus rx. Just check the index, just verify it and let me know, and then we will start like x e to the power mrx, and xr e to the power mrx, something like that, something like this will show up. And still I haven't proved that thing, how that comes, that x square. I'll prove it later, I promise that, but for now you understand this. So this is precisely the theory. So you have a nth order differential equation, so you have a, say, nth order differential equation, nth order dE, you reduce it to n degree polynomial, then you solve it, you get n roots, and you got n solutions to it, right? Now our job is to understand, now our job is to get this n solution, right? So alright, let's do an example for it. Okay, before doing the example, let me introduce, alright, in the example only I will introduce, alright. So example I have y triple dash of x minus of 3y double dash of x plus 4y of x equals to 0. Now I will replace that d to the power n upon dxn with some d to the power n, right, where d is an operator and which actually means n times derivative. So if d is actually defined as d upon dx, and d to the power n is actually n times derivative of some quantity that's right next to it. So this above differential equation may be written as d cube y minus of 3 d square y plus 4y equals to 0. So this may turn out to be d cube minus of 3 d square plus 4 times y equals to 0, right? I mean, this precisely is called as operator method. I mean, I'm making an operator and then using it to solve it, right? So yeah. So so now you want the solution, right? So the idea is you solve this polynomial. So I have this d cube minus of 3d square plus 4 equals to 0, and by hit and trial I say d equals to minus 1 is a solution. So d equals to minus 1 is a solution. So the other solutions will be, so I mean d equals to 1 is a solution, so d plus 1 is a factor of this, and I want you to do the exercise, and I am just writing the result. D plus 1 times d minus 1 times d plus 1. This will be the factors of this above polynomial. So the values of d will be one of these. D will be either 1, minus 1, or 1. Alright, so the solution will be, general solution y will be a e to the power x plus b e to the power minus x plus c x e to the power x. So this is precisely the solution of this differential equation. Now we can do a couple of more examples on that, but I would encourage you guys to go and check for more examples. Now I'll talk about a more general thing now. So far we talked about homogeneous differential equations. Alright, let me stop here. I'll talk about that part in the next video, or we can do one more example right out here. So let's try to do an example, one more example. Alright, say I have a differential equation. Now that I have to think of the third order differential equation, it's a little hard actually. I don't have anyone right off my head, but let me write down something like that: d minus 3 whole cube of y. So this is a notation, right? And so if I break down this notation, that will become d cube plus 9 minus of 3 d into 3 into d minus of 3. Wait for a second, let me check the formula actually. I don't remember a minus b whole cube. I think I'm correct. So that will be d cube plus 9 minus of 3 d square times 3 plus 9 d times 3 equal to 0. That will goes as d cube plus d cube minus of 9 actually, come on, see, minus of 9 d squared plus 27d plus 9 equal to 0, and this whole will be multiplied by y. So the differential equation will look like d cubed y upon dx cubed minus of 9 d square y upon dx squared plus 27 dy upon dx plus 9y equal to 0. So this is actually a condensed form of this differential equation. So alright, let's solve this differential equation given above. Okay, so there is d minus of 3 ka whole cubed times y equals to 0. So you have d equals to 3 as a solution, but since there is just so accordingly the only solution you have is e to the power 3x, but since it's a third order differential equation, you should have 3 solutions. So the other solutions will be x e to the power 3x and x square e to the power 3x. Now it's your job. I mean, you can put x e to the power 3x and then check if it's a solution or not. My claim is it is, and you can check x square also. I mean, you can check it, you should check it once at least, and later on I'll prove that they both are. So alright, so this was one of examples, and with this I end my video here. Thank you for watching.